It's my pleasure to share with you today some of the work we have been doing at the Jet Propulsion Laboratory in Southern California. And the title of my topic today is Defining Viewpoints for Ontology-Based DSLs. And this work is part of the work we have been leading in the context of a project called openCAESAR. This project is meant to modernize the practice of systems engineering using model-based approaches. And in particular, when we say model, we here adopt the notion of ontology as a model. And for that, one of the main contributions of this project is a language called the Ontological Modeling Language, which I will be talking about. Okay, so first to set up the context of my talk, and the motivation for creating the openCAESAR project is to modernize the practice of system engineering. What I'm showing here is the journey for system engineering for typical organizations. On the left-hand side, you see what I call document-based system engineering. This is where a lot of the industry is still at. They're using expressing engineering like artifacts, like requirements, and sometimes design and other artifacts in documents, which are good for human consumption, but not for machine. Of course, there was a movement to formal approaches that has started maybe 20 years ago, and that resulted into what we call model-based system engineering. And there's a lot of tools that have come up to serve this area. However, these tools today are still siloed, and they each have their own representation of information. And to use them together into one context is a bit of a challenge, especially that there is no unifying approach for working with them. So, but I would say the industry, there is maybe 10 to 20% have adopted model-based system engineering. And including, of course, at the Jet Propulsion Lab, we were like early adopters. But the vision we are cruising toward is what we call integrated model centric engineering, where there is, for a given organization, there is a methodology that is defined with models, or in what you will see today, ontologies, that is reflecting how they do the system engineering practice. And then it is also used to make all the tools that are used in the organization work, or the way we get them to interoperate is to connect them all to this common ontology for the organization. And each tool will play a different role in connecting, in providing the information required in this engineering context. So the openCAESAR project was created to facilitate this process of moving towards integrated model-centric engineering, which is, by the way, the name of my team at JPL also. So the openCAESAR project is pushing forward this paradigm of modeling using ontologies, in particular semantic web ontologies. And it provides building blocks to do that, and to provide analysis capabilities that start from ontologies. So one of the first question we had to answer is how do we create ontologies? And in the next chart, I will show you the motivation for defining what we call the ontological modeling language, which is, think of it as a bridge between the modeling world and the semantic web world. It enables an organization to define a set of vocabularies, semantic vocabularies for the system engineering practice. And that could be based on standards or not, depending on the methodology of the organization. But once you define this set of vocabularies, then openCAESAR has capabilities to give you the system engineering functions that you would expect. ability to author models based on the vocabulary, ability to fragment your models into separate data sets, give it to separate authorities, and then integrate them. And by integration, we mean analysis. And then the ability to provide reports or viewpoints to inspect the information. And doing this all in a continuous integration and delivery paradigm that's very prevalent in software engineering. And openCAESAR is bringing it to systems engineering. So openCAESAR is a platform. It's not by itself like meant to be to have an end user tool. It's meant for a platform for toolsness to use to build end user tools in the context of system engineering. Okay, so this brings me to the ontological modeling language. This is the lingua franca of openCAESAR. And think of it as a language to allow you to model two kinds of things. You can model the vocabulary, the semantic vocabulary of your engineering methodology. And then you can use that vocabulary to create descriptions of your system. So it acts as both cases. In the first role, creating vocabulary for your system engineering, I would say that it's kind of playing the same role as, for example, MOF or ECOR is playing, except that it's adding extra value on top. For example, the first one is that it's being rooted in description logic. So the meta model, let's say, that you create, or the vocabulary you create, has description logic semantics, which allows you to generate inferences. It allows you to state your assertions, but also have some logical inference semantic to generate other things that you did not say explicitly. And this allows you to be concise in what you want to say. You don't have to explicitly say everything. Let the rules generate these inferences. And it also works with over-the-shelf reasoners, DL reasoners, that can check the consistency of your system description based on your semantic vocabulary. It also had the side effect of simplifying queries, since if you can generate inferences, your queries can be more direct instead of having to embed your inferencing logic in the query itself. Another benefit for like ontologies is componentization. It allows you to break the kind of knowledge or information you want to say based on a methodology, and it allows you to group the information that you want to say by viewpoints in a much finer way that you can do, for example, with ECOR. Another thing is the extensibility, meaning it allows somebody to define some concepts and talk about it, but then someone else to come and extend that and say extra information about them that the original author did not say about them. Think of this as, let's say you're modeling a system and you can model the nominal scenarios, but then another team responsible for the off-nominal scenarios can come and add extra information about this system. So why did we create OML when other languages like OWL from Semantic Web exist? We started actually with that, and we found it a bit lower level than how people from modeling background think about it. What we ended up with is discovering some set of patterns of using OWL that allow you to properly model, especially that OWL adopts this open world assumption that makes it a bit tricky to formulate what you want and get the reasoner to give you results. So the OML is a DSL basically that is around this set of patterns, and it can produce the corresponding OWL. So we use it as like a compiler into OWL. Okay, so how is OML implemented? We provide an EMF-based implementation of OML. There's a meta model, but there's also a textual syntax, which is the main like user-based syntax to create OML models. But beside the textual syntax or index text, There is also XMI, the regular XMI, and also the adjacent representation. So, and the Java API. With this, we published 3 artifacts. We have an Eclipse update site, which allows us to, thanks to Sirius, produce rich like IDEs using Eclipse. We also produce a Maven Java like jar that we also use to develop a lot of analysis tools based on OML. We also publish a language server for OML, which allows it to work in any IDE that supports language servers. And we use some other technologies like Sprotty to create diagrams quickly in any IDE. It becomes like a diagram server. Okay, so I will be focusing mostly in my talk about the Eclipse-based environment that we developed, and we call it Rosetta. So Rosetta is the name of the plugins to Eclipse that allow you to work with OML in Eclipse. And we both publish update site and a complete like RCP application that you can download from the openCAESAR project. And you see here what you would expect in a typical modeling workbench. On the left, you have the Explorer that allows you to create OML files. And we have a particular OML project template that allow you to define the sources of the ontology that you want to work on, but also declare their dependencies, which we use Maven to manage. So basically, an OML project is both a serious modeling project and also a Gradle project. With the Gradle artifact, you declare dependencies on other OML libraries that have been published to Maven, and you can also publish your own like OML dataset to Maven for reuse by other projects. This way, the management of dependencies is very similar to how you would manage, for example, Java dependencies in your Java application. And we have the main textual editor for text-based that allow you to author ontologies with textual syntax. But we also have the Sirius viewpoints on top that allows you to both visualize, and more recently we also added the authoring features directly into the Sirius representations, including, of course, diagrams, tables, and property sheets. So this is how it would look like in Eclipse. Okay, so what can you do with that? An OML project basically defines a semantic web dataset. It's a dataset that could be of 2 kinds: either vocabulary, which is like class diagram modeling, it's like the meta modeling, and then you have also the system descriptions, which is like the instance, the user models, where you describe the system. However, with ontologies, you can nicely layer your meta models or define them into layers that build on each other. In effect, what you are building here is a stack of ontologies that define your architectural framework. At the very top, you see the core part, which is just a set of standard libraries from the public domain that you can use in your methodology. Next, you define the framework or the foundation design patterns for your methodology. And here you can define your own foundation or use one of the standard foundations out there like UML, SysML, Capella, and others. Then on this foundation, you build your specific practice in system engineering. For example, if you are modeling cyber physical systems, you would expect you to talk about mechanical aspects, electrical operations, VNV, INT, and all these concerns. You can model them with ontologies by specializing the foundational patterns. And finally, since we are talking about work being done by certain organizations, programs, teams, we can integrate these separate domains together into applications that can be given to projects or programs to work with in defining their systems. they use now the stack of ontologies to describe the system that they want, and they can break it up and federate it into various pieces and use the Maven dependencies to establish connections between each other. I'll show you what typical vocabulary looks like on OML. On the right-hand side, you see a vocabulary defined as a global unique namespace and a local prefix for that namespace. Vocabularies can extend each other, can import each other, so they can build on top of other vocabularies, or they can also use some standard library of instances, descriptions. A vocabulary defines terms, so think of vocabulary as like a terminology or a meta model. So it defines terms. These terms could be classes, data types, properties, or relations. So although the original OWL only has these abstractions, in OML, since it's like a methodology of using OWL, we extended these concepts into aspects, concept, relation, entity for classes. Data types could be either scalar or structure. Properties could be annotation, scalar or structured. And relationships can go into directions forward and reverse. You can also use a reference mechanism to refer to terms defined by other vocabulary, and you can add more information about them. We call them axioms. And you can also define rules, which means extra inference rules that you want to add to your domain. This is what the vocabulary can do. And as I said, it inherits this open world assumptions from OWL. However, when you actually use it in a particular context, you want to close the word on it to make the reasoning make sense. And we introduced this concept of a vocabulary bundle that is kind of, it closes the word. It says what we are modeling with our methodology is made up of these vocabularies, and you can list them here. Bundles can also extend other bundles to elaborate the methodology. So what does an instance of a vocabulary look like? For example, here I'm using an architectural methodology called state analysis, just as an example. Of course, it's much elaborate than the example I'm showing, but I chose to establish some base framework first that introduces something called a container and a contained element, and then a contains relationship between them from container to contained element. And in one direction, it says element contains another element. In the other direction, it's contained by it. And you can see some semantic flags that I can turn on this relationship, saying it's inverse functional, meaning that the target can only belong to maximum one source. Asymmetric, meaning if a container contains some element, the other element does for sure will not contain it. And irreflexive, meaning an element cannot contain itself. Then, based on this foundation, I'm building the state analysis vocabulary that extends the base and then uses it. For example, it defines something called the system under control, which is a container, and it restricts what it can contain to physical objects. Again, physical objects is container, contained element, and so forth. And then it introduces two relationships. Characterizes between a physical object and a state, and affects from one state to another. So in order to allow the user to author such thing, we provide a vocabulary authoring viewpoint using Sirius. So think of it as the viewpoint is referencing the OML meta model, OML API, and it defines a viewpoint that gives allow you to model or visualize, if you have modeled it with Xtext directly, your vocabulary, in this case state analysis. And then once you do that, then you can describe the system. You can actually now describe some particular system using it in what we call description. So in a description, again, like other ontologies, has a namespace, and then you can say explicitly which vocabulary you are going to use here in the description. You can reference it, and descriptions can also extend each other. So think of, I created a user model for something, somebody else can come and say, I want to extend, when I say more about what you just said in my own context. So ontologies are like a namespace for an authority to say what they want about it. And that's a nice feature of ontologies, that the unit of the building block is a statement about something, which you can put into your own context. So it allows you to talk about instances that are typed by types from vocabularies, and allows you to also reference an existing an instance defined elsewhere to say something more about it. And these instances could represent concepts or could represent relationships. So you can, for example, reify a relationship between two concepts and say and characterize it by its own attributes. And as an example of using descriptions, it's a case study called Small Body, which is like a mission, a space mission to an asteroid to navigate and land there. So we want to describe the system under control in the state analysis methodology. So we say it's containing we have a system under control called Small Body, and that one has also a spacecraft that belongs to this system under control, and there is a few equipments, devices on the spacecraft, like an onboard computer, solar panel, and whatnot. And you can see here the vocabulary, the base and the state analysis vocabularies are being used in describing the system. You can also talk about the states of these objects. You can say the spacecraft has several states, like size, shape, and attitude, and they characterize the spacecraft. And then in a separate model completely, you can say how these states affect each other, how the physics work. So you can start referencing states. For example, this model introduces the states. This other model says, by the way, that state is affecting this other state. So based on your methodology, you can break up the information into views. And actually, in my example here, when the developer of this ontology thought about how to go about organizing the methodology, saying, first you define the physical objects, then you define the states, then you say how the states affect each other. And for each one of those, they want to develop a viewpoint, a Sirius-based viewpoint that allow them to describe the information in this step of the methodology. So the result would be another Sirius-based viewpoint specific for this methodology that you have defined with vocabulary. So instead of in the traditional like E-core based, you define a meta model that represents your methodology. In this case, there is one meta model, which is OML, but you define a vocabulary in OML that's rooted in description logic, and then you describe a viewpoint on top of the same OML meta model, but in this case, it's specific to your DSL or the framework you are working with, the stack of vocabularies you're working with. And in this case, like here is a table that allows you, a diagram allows you to describe the objects. Then this table allows you to describe the states. And then this diagram allows you to say which state affects which other state. This way, you can, the toolsmith of the methodology has a full control on which exact statements can be expressed in which kind of model. And the result, of course, will become like OML description models. So in defining those viewpoints, of course, the OML meta model provides APIs, and Sirius, thanks to its Java services facility, you can add extra APIs. So in this example, we've added a little bit extra layer of API just to make it easier to use in the Sirius context. And the developers of the viewpoints refer or make use of these APIs to describe the viewpoint, for example, looking for concept instances that have the type physical object in this case. So you see here, physical object is passed as a string from AQL, which is now then in the API interpreted to reference a concept from a vocabulary. And this point I will talk about in future works, how we want to improve this, since using strings like this loses type safety. So we have some thoughts about how to improve this ability. Okay, so at this point, I will show you a demo of this case study that I have been talking about, which is state analysis, allow you to model system under control and a control system and the interface between them, measurements and commands, and in the control system model the states and their effects and the controllers and like estimators. And we'll use this to define this small body example. All right, so let me show the first video. And I've captured this video in a bit of a fast speed just to be able to show you. And the point of the video was to show that someone who want to define a methodology, use it to define an example, can do this in a very quick and pragmatic way with the openCAESAR tooling. So it starts with creating a vocabulary model with some wizards, and then in this case, I was using the visualizer more, so I was using the Xtext editor to author the vocabulary, and the Sirius viewpoint is put on the right-hand side to reflect what the user is like doing as a visualizer. But the same thing could have started with from the Sirius diagram directly to author this viewpoint. So in this case, we're defining the basic concepts in the methodology of state analysis, system under control, control system, and the fact that you have estimators and controllers and whatnot. And with description logic, you can be very specific about typing and what things can be domain and range of properties in each individual context. Now that we have done that, we can use it to model this heated camera example. And this time we define a description project and say which vocabulary we want to use with gradal dependencies. But then we can start to author the various fragments of our model. For example, modeling the physical objects first, saying I have this system under control. It's made of spacecraft. Spacecraft has these objects. They are characterized this way, effects that way, and so the point here, I was showing that you can do that, but then you can of course use the Sirius viewpoint that you can very quickly as a toolsmith develop to visualize your model and to enable also the authoring directly of your model using ontologies. So here in this part, I am creating on the fly a viewpoint, a Sirius viewpoint that will create two kinds of viewpoints, two kinds of representations: a tabular one to visualize the architecture as a topology, like a containment hierarchy, a composition tree of systems and subsystems and components and their states. And very quickly, one could put together a viewpoint that shows the expected results on the right-hand side here, the table. And then I also defined this diagram, the state effects diagram, that actually visualizes the states and the effect relationship between them, and what measurements and commands that can be, which is like the interface to this system under control. So it's this small demo shows the power of how one can do everything with very declarative methods, with ontologies, description logic, and have all the analysis capability that you can leverage. Go back to my slides. So how is that used in practice? In fact, at JPL, we use a lot, we build a lot on the openCAESAR project. The system engineering practice at JPL. A lot of projects at JPL still use document-based methods, and we wanted to get them out of this into model-based approaches. Using tools like UML, SysML proved to be a bit hard for them to use, coming from their background. They had to learn a lot. It was a big learning curve. Although they, in their mind, what they want to describe is like they follow a particular methodology. So what we help them define this methodology in a formal way using vocabulary, like a domain-specific language, basically. We created for them. We, of course, had to start from some foundation. We actually defined a very small foundation that's focused on system engineering, things like component presents interface, component interface can join other interface, component perform function, and this is the foundation. And then we inherited from that, or specialized these patterns in electrical engineering, mechanical engineering, based on the way they think and work. And then based on that ontology or that vocabulary, we gave them authoring capabilities with the Workbench in a similar way to what I showed before. And in that context, we added a lot of useful features like correct by construction modeling, reusable libraries that some other people can define and you can reuse, automated verification, automated refactoring, configuration management. And that was dramatically better than the document-based approaches they were using. We also developed an analysis pipeline, thanks to the OML analysis tools, where that can check consistency, completeness, correctness of the model. And this correctness could be by simulation, mathematical solving, and other approaches. And this is done in a continuous integration and delivery way with Jenkins. And this results into reports or dashboards or viewpoints that can be visualized on another application called CAESAR Cloud, a web-based application that allows looking at these results.
Nugget, just to warn you, we are already out of time. So okay. I don't know how many slides you have. I think it's okay if we...
I only have 3 minutes. Is fine?
Fine. Okay.
Okay, great. Yeah, so I just want to show you quickly like how this workbench looks like at JPL that we built. It's since they were coming from they were users of Excel, we built for them tabular viewpoints with property sheets that allow them to be very specific about modeling their system. We give them, as I said, out of the box features like correct by construction features that allow them to be very precise and not do a lot of mistakes. They can also do validation, and they can do refactoring very easy using wizards that allow them to express the intent of what they want, and it will perform it to them on their behalf. Okay, for sake of time, I will reach to my future work slide, which is my last slide. So how do we go from here? We have two paths of improvement from here. We want to make it easier for toolsmiths to define those description viewpoints. Currently, we use the Sirius facilities, AQL, but we want to maybe enhance it or adapt it to work with, to identify the types defined by the vocabularies as types that can offer validation support. We want to see if we can make it even easier to generate these O-design models by annotating vocabularies. And we want to have a base viewpoint that can be used as is out of the box, but have it customizable. Another thread we are looking at is going web-based with this capability. So we were interested in considering the Sirius Web, in which case we know that it allows you to publish your models or have your models into a database. So we want to try publishing the OML models into a database, let the user use the Sirius Web session to edit it, and then at the end download the model back into files that to go into configuration management into something like Git. And I think that was the last slide I have today.
Very nice presentation, thanks. And well, you raised a lot of interest here, and we have a lot of questions. So we'll be definitely out of time. Okay, first question we have. Can we do model transformation and all the good things we can do with model-based engineering using
Absolutely,
your OML
yeah. So
tools?
since OML is an EMF-based language, you have the full power of EMF, like the ecosystem to work with. So you can use all transformation languages from EMF on the OML models, but also since OML maps to OWL, and you can have an equivalent OWL ontology, you can also use something like Sparkle Update as a transformation language. So you can do it both on OML or on OWL.
Okay, thanks. Next question. Did you extend Sirius to use vocabularies instead of meta model?
No, we didn't actually extend Sirius itself. Like as I said, the OML language allows you to model vocabularies as instances of the OML meta model, but also descriptions as instances of the OML meta model. Both of them are in the same level. So no, we used Sirius as is to model both vocabularies and descriptions.
Thanks.
How does OML? Yeah. Okay. So this is a very common question, actually.
Sorry.
It's a very common question that I get asked a lot: how OML compares to SysML v2. In fact, the right analogy is OML to MOF, not to OML v2, because I can take SysML v2 and describe it as an OML vocabulary. So the OML vocabulary is like a meta modeling language. So you can use it to describe SysML v2 itself. And then once you define that, then you can define OML descriptions that use the SysML v2 vocabulary.
Okay, and next question: how are you positioning this approach compared to the new OMG-CAESAR language?
Right. So kernel, I also thought about this problem, and kernel itself is like, if you remember, I talked about a vocabulary stack. So kernel is kind of a foundational or core layer in the stack that can be also represented with a vocabulary, and then SysML is another vocabulary that extends kernel. So you can basically map kernel and develop OML vocabularies for kernel and SysML v2, and then your description will become like use instances of those vocabularies. So I think this stack supported by this SysML v2 can be realized in ontologies.
Okay, I think we had a lot of questions. About the, let's say, so do you have specific resources to recommend?
Right. There is a tutorial that it's like a mini workshop, 2-day workshop that covers all the background necessary to get up to speed on OML, that I can leave the link if there's a way to share the link with the group. I can post some links to this material. The workshop has a series of mini demonstrations inside that walk you through building a methodology, and then as a set of design patterns, and using it to describe a system, and then incrementally add to the method to the vocabulary, and add further and further details, and use the full paradigm of analysis, generation of report, and do this continuous loop. I can make it. It is already public, but I can make the link available to you. And there is also another workshop I can reference, a recent one at the OMG 4-hour workshop, where I also deep dive into some of these topics that you can also leave a link to. A good source for this will be the openCAESAR blog. So if you Google openCAESAR.io, you'll find the blog, and with a lot of these materials I'm talking about published there.
Okay, thanks for that. We have a lot of those questions that we will forward you them. I've just one last question. I'm just wondering if your work is related with basically the same issue are facing your colleague from the ESAR. They are also developing their own ontology language and tooling named ORM.
Yes.
And things like that. So have you exchanged with them?
Yeah, I've actually presented the openCAESAR to them 2 years ago, maybe before the pandemic, and it was a good interchange. I didn't have a chance to follow up with them and try to synchronize, but I think I heard there's a new project starting around that, so it will be a good opportunity to correspond and maybe share ideas. And by the way, I've also did a prototype of modeling Capella and Arcadia with OML. I can share this prototype for whoever is interested.